So, on April 5th, 2017, Marina S. Vyazovska published a really interesting proof about circle packing in 8 dimensions. I'm sure this is probably the first time a lot of you are hearing this information, and this discovery still probably doesn't mean anything to you. I mean, why should it? Well, understanding higher dimensions can actually be really helpful in situations that don't even seem mathematically related. But first, we need to understand what a dimension actually is, so we'll get back to real-life application later. A dimension is a mathematical space that is defined as the minimum number of coordinates needed to specify any point within it. Simple, right? If we break that apart, we can actually realize that a dimension is defined as the amount of points that it takes to find a place or point. Let me give an example. The zeroth dimension would just be a point. There are no directions you could go. The first dimension would be a collection of points to form a line with one direction, left, right, depending on how you look at it. The second dimension would be a collection of lines creating a plane. This would have two directions, up, down, and left, right, depending on how you look at it. The third dimension would be a collection of planes, creating a third direction, height. This is where we live. Once we start to add more dimensions, it gets a little bit weird. Now that we have left three spatial dimensions, people start to perceive the fourth dimension as time. But another way to imagine the fourth dimension is an extrusion of the third dimension, where we can go forward and backwards. So now we have length, width, height, and time. So how can I imagine this if I can't see it or be there? Well, there is a little trick to help you imagine it. Think of it as an analogy. The fourth dimension is to the third dimension, as the third dimension is to the second dimension. So, to a four-dimensional being, the third dimension looks a little flat. If we look at the perspective of a two-dimensional person living in the third dimension, they would only be able to see slices of a third-dimensional object. So to them, a sphere looks like a fluctuating circle as it moves into a different plane in the third dimension. For three-dimensional humans, we can only see three-dimensional portions of four-dimensional objects, which is why it is hard to project four-dimensional objects into a two-dimensional drawing, which is why we have images like this, or even this, to be able to see a fourth-dimensional cube, better known as a tesseract. As we can see here in this visualizer, as I push the tesseract up and down the fourth-dimensional plane, this fourth-dimensional tesseract changes, because we can only see part of it at a time. This could lead onto a whole other understanding of four-dimensional shapes. As we've talked about, some of the most basic extrusions of shapes in multiple dimensions, or polytopes, are the point, the line, the square, the cube, and the tesseract. So, I bet you're still thinking, how can I use this information? Well, I'm going to lay out a problem for you that isn't necessarily related to this topic, and then I'm going to relate it. Let's say there's a school performance and you are selling tickets for it. There are three ticket categories: student, parents, and the public. You can sell up to 600 student tickets, 500 parent tickets, and 400 tickets to the public, but there are only enough seats for 1,200 people. We can represent it as a list of numbers, or we could graph it to get a better representation of the problem. It would look something like this. You can see here that we have a graph in three dimensions because we have three different variables, the types of tickets. Then, this slant here is a limit of tickets you can sell. If we add another variable, like alumni tickets, let's say 150 alumni tickets, we would need a fourth dimension to graph it, and it would look a little something like this in four dimensions. Obviously, it's a three-dimensional view of a four-dimensional graph in two dimensions being on paper, if you can wrap your head around that. From this introduction to the fourth dimension, I would hope that you've learned at least one thing about this topic and might even want to further pursue it, because there's definitely so much more room, or space, to learn.